So method of Lagrange multipliers. In a nutshell, here's what it is. So when we were optimizing functions, if we have a continuous function on a closed bounded region, all right, then the way we looked at stuff is we found the critical points inside the region. So let's say here's our region R. So we found the critical points on the inside. And then we found essentially the critical points on the boundary. So we went in here and looked at what was going on the boundary. And the way we'd been doing this is we went back to Calc 1 to help us with that. So by looking at what the function looked like on the boundary through whatever means we did, we would take it back into a one-dimensional optimization problem, which we do your Calc 1 or whatever you learned in AP to handle that. What Lagrange multiplier does, Lagrange multipliers gives us a new way to help us find critical points on boundaries. So here's the setup. Suppose f is differentiable and f has a max or a min subject to a constraint g of x, y equal a constant. Okay, so let's sketch the situation here. If we think of z as being a function of x and y, we can visualize z as being a surface. All right? G of x, y equal a constant, we can think of that as being a constraint curve in the plane. Right? So this is the g of x, y equal a constant. Think of that as being in the plane. So then when you lift this up and you look at the lift, let's say you've got a maximum and a minimum. So let's say that's the maximum you get, and let's say that's the minimum you get. All right? So Lagrange's theorem is going to give us places to look for the maximum and the minimum. But sort of going into this, you have to assume that you know there's a max or min defined. Then, let's see here. Then the extreme value, so then the max or the min, occurs at the places where the gradient of f is parallel to the gradient of g, i.e., where the gradient of f is lambda gradient of g for some real number lambda. Okay? Does anyone know this letter lambda? It's kind of the Greek letter. It's like the Greek version of what letter? You know? You know it from Revenge of the Nerds? That's fair. If you take linear algebra, you'll see it. It's the Greek letter for L. So this lambda here, this number is called, this is actually called the Lagrange multiplier. Okay. But yeah, lambda is usually for L or something. But this is actually, that number is actually called the Lagrange multiplier. And a nice little project, and I kind of hint at this, you know, at the end of the handout. There's a nice project that sort of what does a Lagrange multiplier mean? Because in like economics and things like that, the actual Lagrange multiplier has some specific significance. But basically, it's telling you these maxes and mins are going to happen when these gradients are parallel. So let's see why that's true. So suppose f has a max or a min at the point AB. All right. Then that means that g of AB would have to equal that constant. All right. So if f has a max or a min subject to that constraint curve, then g of AB is a constant. And what we're going to do is, since we're assuming everything in here is differentiable, let r of t, and we've seen this before, x of t, y of t, be a differentiable or be a smooth parameterization of the curve g of xy equal a constant. All right, so we're going to use two facts that we actually already talked about last week when we talked about properties of the gradient. All right, property one is that the gradient of a function is orthogonal to all the level curves. So the gradient is orthogonal to the level curves. So what does that mean? That means that the gradient of g is always orthogonal to the level curves of g. So that means that the gradient at AB is going to be orthogonal to the point AB on our curve g of xy equal a constant. All right, so this is something we proved. This was courtesy of the chain rule. All right, so that one we get pretty much for free. So the gradient of g at AB is going to be orthogonal to the curve at the point AB. So we got that one. So now we're going to look at what's going on here with the function f. So if I look at f, it depends upon x and y, and because of the parameterization, it depends upon t. So once again, I'm thinking I've got this surface here. I've got my function g sitting underneath it. And now I've parameterized it. So then r is the parameterization of this. So when I lift that up, now you can see we've got the lift up there, and so f is ultimately a function of t. T goes in, gives you a location on the curve g of xy equals c, and then that gets popped up, gives you the z value. All right. So I can think of f as being a function of t, so I can take the derivative. All right. And how do I get to t? I can go via the x or via the y. So I use chain rule. Chain rule says I take the partial derivative of f with respect to x times the derivative of x with respect to t plus the partial derivative of f with respect to y times the derivative of y with respect to t. And let's suppose that t naught corresponds to the point AB, which is where we're having, either the max or the min, one of the two. Right? So let's say it's a maximum. Now I can shift the parameter as much as I want. So if you go back and look at the parametric tricks of the trade, you can shift the parameter so that this, say, maximum not only is the absolute maximum, but it's the relative maximum or local maximum. All right, we can just zoom in so it's a maximum there. And so f has a local max at t naught. And so what do you know if you have a differentiable function and you've got a local maximum? So thinking back to Calc 1 or AP Calc, if you've got a local max of a differentiable function, what's the derivative there? Yeah, first derivative is 0. All right? So that means that if I look at this expression, when I plug in t equals t naught, that's going to be 0. So what would that look like? Well, the partial with respect to x at t naught would be ab, x prime at t naught, plus the partial with respect to y would give you fy at ab times y prime of t naught is equal to 0. And by golly, what do we have? That's the gradient at ab dotted with x prime at t naught, y prime of t naught, and x prime at t naught, comma y prime of t naught that's r prime of t naught. And so here's another vector that's orthogonal to r prime. So the gradient vector is orthogonal to r prime at t naught. And remember, r prime is a tangent vector at the point AB on the curve. So what we've just shown is if I look at my curve here and it's as it's parameterized, there's the point AB. I've shown that the gradient of f is orthogonal to that. So now we've got two vectors that are perpendicular or orthogonal to the same vector. So we've got the gradient of g and the gradient of f are both orthogonal to r prime at t naught. So that means that they are parallel. So that's the analytic argument, whoops, to the multiplier theorem. Okay. Now, to get a geometric intuition as to this, we can also think about this geometrically in terms of level curves. So here's a scenario here that's got it sort of drawn out. So the mesh surface here, that's your z equals f of x, y. And then you've got your constraint curve, g of x, y equals c. And once again, we've got the lift on up to the surface. You can see the biggest z value on here is going to be at this point, and the smallest z value is going to be down here. All right. So another way to think about this theorem is we go once again to the contour maps. And so these concentric circles, this is the contour map of z equals f of x, y. So as I go through here and start slicing this, Right? I'm going to get these concentric circles. And so the biggest and smallest z values in this particular case, they're going to happen here and here. This is when the contours of f just touch the contour g. This is the first time they touch, so this, in this particular case, since the function is decreasing as we move out, this is going to be the innermost contour. And so if the contour here just touches the contour there, that means that they would have the same tangent. So if they have the same tangent, then that means the normal vectors have to be orthogonal. And we know that the gradient of f is orthogonal to the contours, f of x, y equals a constant. And we know the gradient of g is orthogonal to its contours. And so that's another way to think about this, is as you're looking at your contours, where you first meet the constraint curve, that's going to be your maximum or minimum value. And at that point, they have the same tangents, which means the normal vectors would be orthogonal. All right, and here it is all mapped out, the proof. It's a good proof to kind of go through because it brings in all the big players we've had in this chapter, to be honest. It's got the gradient in there. It's got the notion of parameterization. It's got the notion of lifts. So there's a lot of goodness in there. All right, long and short of it is the method of Lagrange multipliers. And once again, we will work problems tomorrow with this, and then we'll talk about generalizations and talk about how we could use that to help us with the box problem. But the first thing you have to do is establish that you've got a maximum or minimum or both. So this is where you have to. This is where some of the heavy lifting is. If you're optimizing a continuous function over a closed bounded interval, the extreme value theorem comes in to just tell you you're going to get a max or a min. But with Lagrange multipliers, you have to sometimes just apply what's often called common sense or number sense or something like that. So make sure you know you've got a max or a min. And then you set up the following equations. Now, if you're in 2 dimensions, this is how you set up the parallel condition between the gradients. You're going to get a system of 3 equations with 3 unknowns, because now you've got the lambda to go after. So you look up how are 2 vectors equal, you equate their components. You got the fx is lambda gx, the fy is lambda gy, and g of xy equal a constant. So you got 3 equations and 3 unknowns. So what you've done is in order to avoid the calc 1 stuff on the boundary, where you take the function, reduce it to 1 dimension, and then do 1-dimensional calc on it, now you're just doing like higher dimensional algebra. So there's always this trade-off in math, right? So you're going to do less calculus with this method, but you're going to do more algebra. And then Lagrange theorem says the location is going to be among the solutions to this system. So you're going to get some answers here. The biggest answer you get is going to be the max if you've argued there's a maximum. The smallest answer is going to be a min if you've argued there's a minimum. So it's kind of like when you had Fermat's theorem in Calc 1, you get a list of candidates. If you're going to have a max or a min, it's going to be one of these that we get out of the system. Okay? All right, so example 1 here, let's work through the details on this. We're asked to optimize this function subject to this constraint. So optimize here means find both the max and the min. Now hopefully you recognize this. What kind of curve is this going to work out to be here? kind of curve is that going to be? You recognize it? No, not an S curve. So how many variables are squared? 2. Do they have the same or different coefficients? All right, so it's going to be a circle. All right, if it's going to be anything, it'll be a circle. Now, what we know about circles, so once again, this is living here in the xy plane. Circles are a closed bounded set. Okay? It's bounded because it's within a finite radius, and it's closed because, well, it's just itself. It's an edge, right? So it's a closed set. So the extreme value theorem guarantees there is both a max and a min. All right. So when they tell us to optimize this, okay, we can be sure that there is a max and a min defined. So here's how we do it. We have our objective function. The function we're trying to find the max and the min, that's the objective function. That's the f of x. And for our constraint, all we need is the constraint written in the form g of x, y equal a constant. Now, it doesn't matter what that constant is, because we're going to be taking the gradient. So if you want to move the 3 over or not, it doesn't matter, because when we go to find the gradient of g, the constant will drop out. Okay. All right, so we need to know where the gradient of f is parallel to the gradient of g. So that's going to tell us where where fx is equal to lambda gx, fy is lambda gy, and then the last equation is going to be g equals c. So here we've got 3 equations and 3 unknowns. So let's look at the fx equal lambda gx equation. So what's the partial derivative of f with respect to x? Minus 2x. And likewise, so yeah, we'll do the minus 2x here, equals lambda times, now I need the partial derivative of g with respect to x. (2x minus 4). So that would be the parallel condition in the x component, y component now. Fy is lambda times gy, and then I still have my constraint, which ties the x and y together. So here's our system of equations. So we've got equation 1, equation 2, and equation 3. Okay? Now, even though we're not going to do much with lambda in this course, we need to make sure whatever we have for x and y will produce a lambda. And once again, that's a great project, is what's the lambda mean? At the end of the packet, there's some there's a problem that sort of leads you into that. But like I think in economics, lambda plays a role in what you're trying to do there. Okay, so we got the classic substitution elimination kind of a thing. Basically, you look at these equations and you just pick one that looks like it's easy to work with. So We got equation 1, equation 2, equation 3. Which one do you want to start working with? So you've got to figure out what x, y, and lambda are. All right, if we start with equation 3, is it easy to solve for x or y here? What about like equation 2? Is it easy to solve for lambda or y here? Or equation 1, x or y? So yeah, if we start with 2, and once again, we're just trying to, we have substitution and elimination. Those are the tools we have here. If I look at this one, if equation 2, I got minus 2y is 2y lambda. Now, it might be tempting, and you still could do this. What could you do to both sides? Yeah, you could divide by 2. So that makes it easier. And then we can move everything over. I can add the y to both sides. Y lambda plus y is 0. And factor the y out. And so now I'm going to get two cases, right? I've got y times lambda plus 1 is 0. So case 1, I'll do Roman numerals here. Either y is 0, or case 2, lambda is what? Yeah, -1. Okay. Now the key to these types of systems, I think, is just keeping yourself organized. So one thing I want to point out, you know, it might have been tempting to divide by 2y, but when you divide by a variable, you need to make sure that the variable can't be 0. So if we were to divide by 2y here to get lambda's -1, you'd have to have the case y equals 0 anyway. You follow? So now we go through the different cases. Let's do case 1. Case 1, y equals 0. That means what you do is in all of the equations that are left over, 1 and 3, you plug in y is 0. Now in equation 1, there is no y's, so equation 1 is going to stay the same. So minus 2x is lambda times 2x minus 4. But equation 3 now is going to be a lot easier. When you plug this into here, look what you get. You get x squared minus 4x plus 3 is 0. There it is. So now equation 3 has just x in it. We can solve this. How do you solve such an equation? Yeah, you factor it. Factors of 3 that add up to -4. So what do I get for x here? 3 or 1. Good. Okay? So now, as far as x and y are concerned, I've got 3, 0, and 1, 0. So these are my solutions, x and y. But I need to make sure, even though I'm not going to really use the lambda, I need to make sure I can get a lambda out of each of these cases. So I can go up here to equation 1 then. And when x is 3, I get a -6 is lambda times, what would that be? 2? So lambda is -3. And then when x is equal to 1, lambda equals 1. Okay? Now once again, what do those lambdas mean? That's a nice little project. Okay? But the fact is we need to have solutions to the whole system for these to be considered the critical points. So even though you're not going to use lambda, you need to make sure that there is a lambda for each of these points. All right, let's go over to case 2 now. Case 2, lambda is -1. So now I'm going to go back to, in this case, equation 3 is not going to be any different because there's no lambdas in there. But let's look at equation 1. If I plug in lambda is -1, I get -2x equals -1 times 2x minus 4. And so what happens here with equation 1? What happens to the 2x's? So I get 4 equals 0, which means that there's what? There's no solution, okay? So there's no solution here. So the lambda equals -1 didn't give us anything, all right? So looking back, if you had divided through by the y and not made y equals 0 a special case, you would have gotten no answers from this system. So that's why it's really important that if you do divide by a variable, you make that a special case of when that variable can be 0 to see if you're missing anything. So here's our 2 critical points. So according to Lagrange's theorem now, we're good to go. So we know the EVT tells us that there's a max and a min. And so we plug in the points we get. We got f of 1, 0. F of 3, 0. And we're plugging these into our function f of x, y. What was the original function? 12 minus x squared minus y squared. Nice friendly paraboloid. That's 11. 12 minus... It's going to be 3. So since we're guaranteed a max and a min, this number must be the what? That's got to be the max, and this must be the what? Min. You follow? And as I mentioned yesterday, this is exactly the situation we have here. So the top point here is the point 1, 0, 11. This is the point 3, 0, 3. Okay. And you can see here so this would be the contour z equals 11, or that would be the plane f of x, y equals 11. That's the contour there at the plane z equals 11. Here this is at the plane z equals 3, so that's the contour f of x, y equals 3. Okay? You see how it all connects or not, folks? So I think I mentioned yesterday in the previous book we used for this, Larson, I think it was Larson, they said that the equations that you get from Lagrange multipliers are going to be systems of nonlinear equations. Now, to be honest though, the systems you had from last section are also systems of nonlinear equations. But these things can be unruly, all right? Most of the time you won't be able to solve them. But when you go through the methodology, you just want to keep yourself organized with cases. That's the best advice I can give you. All right, let's look at another example here. Maximize this function subject to this function. Why is there no minimum? Okay. Hint, before you get started, rewrite the constraint in this form. So maximize, remember maximize, this is our objective function, what they're maximizing. Subject to is our constraint. So the f of xy here is what we're trying to maximize. And our constraint is y equals 2 minus x squared. Now in order to use the method of Lagrange multipliers, we need to rewrite the constraint essentially so it looks like the contour of a function of two variables. In other words, you've got to get all the letters on one side, and you can do this however you like. What's one way to rewrite this so it's of the form g of xy equal a constant? Yeah, you can just add the x squared over. Okay, so if we do it this way, we identify our g of xy is y plus x squared. Could you subtract the y over? Of course. And then your g of xy would be 2 minus x squared minus y. Is it going to matter? No, because the gradient of one would just be the opposite of the gradient of the other. And two vectors being parallel, you're allowed to have one be plus or minus the other. So it doesn't matter how you arrange your g, you'll get the same critical points in the end. Okay. All right, now we set up our system. I need fx to be lambda gx, fy to be lambda gy, and then we have our constraint. Okay, so here we go. Fx, same fx and fy as before, negative 2x, negative 2y. Lambda gx, what's gx here? So what's the partial of g with respect to x as we've written it here? To x. And then what's the gy as we've written it here? 1. And then we got our constraint. Y plus x squared is 2. And once again, it's good practice to label the equations. You know, and as you're working through your homework problems, please label the equations, and just the easier it is for me to follow, the better it's going to go for you. Okay? Even if you have a mistake here or there, if the process looks right, chances are you'll lose maybe a point at most. Right? But just keep your work organized for me here. All right, now we're just going to pick one to work with. If you look at equation 2, we've got lambda in terms of y already, so that's nice. I mean, that's a freebie. Lambda is minus 2y. So I can now plug that into equation 1 in equation 3. Well, there's no lambda in equation 3, but I can plug this into equation 1 now. And I would have minus 2x is minus 2y times 2x. And so now I have the system. I got the new equation 1, and then I've got the old equation 3. Minus 2x is minus 4yx, or minus 4xy. Then I've got y plus x squared is 2. So I can work on equation 1. So what could I do to simplify equation 1? Or how do you want to proceed here? Yep, we could add 2x to both sides. So we would get 2x minus 4xy is 0. And now we can factor. I can pull out a 2x from both. If I factor 2x out of the first term, I'm left with a 1. What am I left with if I factor 2x out of the second term? So from this equation, I get either x is 0 or I get y is what? A half. So now I can substitute these back into equation 3. So equation 3 was y plus x squared is 2. So looking at x equals 0, I'd get y equals 2. So that's one critical point. When I plug in y equals a half, I get 1/2 plus x squared is 2. So x squared would be 3/2. So what would x be then? You're solving x squared equal 3/2. What's your x going to be? Yeah, and then don't forget the plus or minus. And so here we're going to get two critical points, root 3 over 2, comma a half, negative root 3 over 2, comma a half. Okay. Now once again, this is what we're getting for x and y. We need to make sure that we're going to get lambdas out of this. So we go back then, we know lambda is minus 2y. So for the xy point, 0, 2, the lambda here is minus 2y. So lambda be minus 2 times 2 is minus 4. And for xy equals plus or minus root 3 over 2, a half, we would get a lambda to be minus 2 times a half, which is minus 1. So in both cases here, we do get lambdas to go with the x's and y's. So according to Lagrange's theorem, these are the viable critical points. Now we're told to go looking for a maximum. And then we're also said, why isn't there a minimum? So let's take a look at this maximum here. Once again, I'm going to plug these values into the original function, which I believe is 4 minus x squared minus y squared. So we plug in the 0, 2. You get 0 out of that. And notice the x values here, we got a plus or a minus. When that goes in, that plus or minus is going to get what? Regardless if it's plus or minus, the x is getting squared. So whether it's plus or minus doesn't really matter. You'll get 4 minus 3/2 minus 1/4. You could even turn that into decimals if you want. What do you end up getting for that? Two, yeah, 2 1/4. Yep. All right, so we're looking for a maximum. Lagrange's theorem says your maximum is going to come from one of these points. What's the biggest z value we get here? There you go. So the maximum is 2.25 at, we get 2 points, root 3 halves, comma, 1 half. So we'll look at this geometrically, and then we'll see why there's no minimum. But before we move on to that and look at the stuff geometrically, are there any questions on the algebra here? All right, so we got what, like a minute left, 2 minutes left? So let's take a look at this. There you go. And we're looking at the curve y equals 2 minus x squared. So we can do a cheap parameterization of that. T comma 2 minus t squared, comma f of t comma 2 minus t squared. There's the lift. We'll go t from, I don't know, -2 to 2. Check it out. And let's look at the points. We had 0, 0, f of 0, 0, which was 0. And then we had square root 3 halves. One, and then 2 1/4. And then we had the opposite of that. That should be on there. I'm sorry, there's 1 half, right? There we go. And then the other one. Boom. Okay. So, once again, looking straight down the axis there, there's your constraint curve in the plane. It's a parabola. Here's the lift to the surface. You see this one critical point? It's a local min. It's not an absolute min. And then you see these 2 other points are the maximums. But do you see why there's no min, folks? Because this parabola is going to just keep heading down in the xy plane in quadrants 3 and 4, and that just takes these values down the paraboloid. Okay, so that's a nice little visual check there of what's going on. Right, and that's the contour map for you to look at. Okay. All right, so tomorrow we will finish up Lagrange multipliers and once again talk about a couple possible extensions for projects. Have a great rest of your day and happy midterm to you.